Welcome back, my structural analysis friends. In this video, we're going to start to set up for the basics of the load resistance factor design methodology, LRFD. We'll start with a few basic mechanics assumptions, explain some terminology, and then kind of show you an overview of how the different steel design methodologies actually work. This is kind of a very quick overview, so we won't go into a lot of detail, but hopefully we'll give you an explanation of the basics. So without further ado, let's get started. Everything we do when we're doing structural steel design has its roots in basic mechanics and materials, or strength of materials, basic equations. If you may recall, for an axial stress situation, we were always looking at some sort of load by area, which in this case we could often simplify as some P load, internal load, over the cross-sectional area in which it was acting. This is what we call it as a normal stress. Okay, there are some other versions of this, and when you get into bending, that also are normal stresses. If you remember, one of the familiar ones was sigma was equal to some minus my over I type of equation. This will also have its role when we get into looking at flexural cases. But for now, we're going to kind of just talk generally speaking about this idea of stress being some load or force divided by some area on which it's acting. Okay, and then we knew that through the interaction of Hooke's law that a stress would induce a strain, and so we're going to define a strain then as being some final length minus an initial length over an initial length, kind of the percentage increase, if you will. And so that will be our basic strain. Now we're going to kind of put some labels on here. This is sigma, this is epsilon, our Greek characters for that. Okay, so if we kind of look at, well, what is, in the last video, we talked about the relationship for steel, kind of what sigma versus epsilon was. So if you need to review, go back to the previous video and you'll be able to get a better understanding of how these are related to each other. Again, we're talking about ductile metals here, nothing brittle. It has a well-defined proportional limit and a well-defined yield point. And so that's the case for most of the grades of steel that we're going to be dealing with in this series. Okay, so if we kind of go back and look a little bit, there are a couple of terminologies that are always kind of in the back of our mind that are kind of popping up over and over. The first one is this idea of what we call steel ductility. Okay, and that's the idea that is, if we remember from our definition of elastic materials, if I took a member and I stretched it, when I let off the load, it would return to its original shape. That was said to be elastic. Okay, now, in significant events such as, natural disasters, earthquakes in particular, a lot of times we can load a structure beyond its elastic limit. Okay, and so then this concept of steel ductility is basically defined as the ability of a structure to absorb energy or to undergo large deformations before it actually fails or breaks. Because as a structural engineer, the last thing I want is for my structure to get overloaded and to come immediately crashing down, trapping people or property inside. Instead, I want if I'm going to overload, I want to have it to be able to go through long, large deflections or deformations without actually failing or fracturing, because even if the structure is no longer usable, it's still standing and it hasn't come crashing down on top of people. And so this idea of ductility is a very significant idea, especially with regards to things like connection detailings, and there's a lot of research that's gone into ductility design and the connection detailings and those kind of things. We won't talk a whole lot about that in this class, but we do need to keep it in the back of our mind and have an awareness of it as we go through. All right, we talked a little bit last time about the proportional limit, okay, and this was basically where the end of the linear region on a stress strain curve was. So it would be somewhere kind of like this. If I have stress versus strain, then we had a linear region up to the proportional limit, and then it went nonlinear and started to do other things. But within this region, Hooke's law was valid. That means that the slope of this stress versus strain curve was e to 1, okay, where E is Young's modulus, okay, and that's very important for us as we start to look at it. Again, as we said in the previous video, we like to design for the elastic region so that as loads come and go or the loads vary, that we stay within the elastic region so that when the loads are finally gone or removed, or they go away because the wind died down or whatever, that the structure is in its original deformation and hasn't experienced any permanent strains or permanent deformations, if you will. And so that's a very, very important concept for us. as well. Another term that you'll hear is the idea of a linear structure, okay? And so it's very similar to stress and strain, but if we were to plot a load versus a deflection, okay, then we could say that the slope of this line, if it's linear, would have a constant K value. Okay, and that actually kind of comes out of a Hooke's law derivation, and we'll show you that when we get into tension members. But the idea here is that if I have a point here in which I have, say, 100 pounds, and I had, so let's just say 1 inch of deflection, if I double the load, then I would get that same doubling of the displacement. That's what we're talking about as linear. We don't want a case where as deflections get larger and larger, the load is not to the same ratio, if you will. Okay, and so this is going to be our linear load versus deformation will be our definition here. Now, structures like cable systems, even suspension bridges to some degree, are not linear structures. They still function, but they have to be designed a little bit differently than what I'm going to show you. So we're looking at relatively simple cases in this series as we try to explore the LRFD equations that we're looking at. Now, one of the, if I fold this up a little bit, some of the major assumptions that are behind all of the equations that we're getting ready to do can be summarized by the acronym LEIH. Okay, the L stands for linear. I've explained that one. That's the P versus delta relationship, that it's if I double the load, I double the displacement, triple the load, triple the displacement, so forth and so on. It's a straight line graphic response on this. The elastic E is elastic, which that is our stress versus strain relationship that we showed you. The other two that we have are this idea of I being isotropic, meaning that the material properties themselves do not depend on direction, okay? And that H is homogeneous, meaning that the property is not a function of a position in the structure. Okay, now these are kind of subtle concepts, and we're not going to do a whole lot with them, but we're just going to recognize that these are the assumptions that we're making, and for the most part, they're reasonably valid for fairly rigid materials like steel and concrete, which are common civil and mechanical engineering materials. If we get into things like, plastic or putties or something like that, then these two guys can start to change, as well as the others for sure. Okay, but we can start to violate some of these. Okay, but for us, we're going to make the assumption that that's valid, and for steel, typically that's pretty accurate. And what this allows us to do, if I can maintain all four of these, then I'm allowed to make an assumption of something called small displacement theory being valid. And basically what that means is that if we remain linear, elastic, isotropic, homogeneous, and our deflections are small enough on there, then we can basically say that our delta displacement is approximately equal to 0, which means that by, for the most part, we can say that the object is rigid. Okay, and that's important because if an object is rigid and the displacements are small or approximately 0, this defines a static case, which means that our basic statics equations are now valid. Okay, now if you get into research or into a lot of theoretical computations, this will not be the case. Okay, they'll have large displacement research in which things go into what we call the inelastic region, and things start to deform differently, and you have to do some things a little bit differently in the analysis of those. But for us, again, we're keeping it fairly simple. But these four items, LEIH, give me small displacement theory. Okay, because we're assuming displacements are very, very small compared to the dimensions of the member itself. To give you some idea, imagine a beam that is 30 feet long. If it's 30 feet long, then most design codes say that you're allowed 1 inch of deflection on this member. If it's an L over 360 type of case. Again, we'll talk more about this when we get to serviceability. But if you think about a 1 inch displacement on a beam that's 30 inches or 30 feet long, that's a very small number compared to the dimensions of the object. Okay, and so for us, we can say, oh, well, our assumption of small displacement would be valid for that as well. Okay, so a lot of design codes are setting prescriptions on maximum displacements that are allowed on members, recognizing what these dimensions usually are, and an assurance that we hit that requirement for small displacements. Okay, and so that's kind of a little bit of trivia behind the scenes of what it is that they're trying to do. So those are some of our major assumptions that we're going to be dealing with. Okay, once all this is true, now we can start to talk a little bit about the load and resistance factor design methodology, okay, and the methodologies that are outlined in the book. Okay, so what we're looking at in the book is we're looking at section B3.1 of the specification. Okay, in the 15th edition, this is on, let me make a note here, 15th edition, it's on page 16.1-12. So if I pull the book up here, and we'll kind of come back here. We'll come back and forth between, but I just want to show you. We are in, this is chapter B of the specification. We're up, 16 is the specification itself, and we're looking at this area. Okay, and so these are the basic equations that we're going to look at, and you'll see that my notes match this with some extra stuff that's on it. But what the code is basically saying, if we kind of look at this, and I don't want to get into the habit of just reading from a code manual, I want to try to explain what's going on, is that this is the heart of what's happening in the LRFD method. It says that this RU stands for my required strength using LRFD load combination. So these are my loads with any sort of safety factor applied to them. Okay, and then Rn is the nominal strength of the member using our mechanics principles. So what it's saying is it says that we want the nominal capacity of the member to be greater than the applied loads. And that makes sense, right? It's kind of like if a bucket is your capacity, I don't want to put too much water in the bucket so that it overflows. Water being the load that's being applied or the energy that's being sent into the system. Now, to further protect us, LRFD prescribes this phi factor in front. Okay, and phi is called as a resistance factor. Okay, so the product of phi Rn is known as the design strength. So all of these terms are very, very important. There's a difference between nominal strength, which is kind of the theoretical maximum from our mechanics materials approach, and then phi Rn is the design strength, which is the strength that I'm allowed to count of this. Okay, phi is always a value between 0 and 1. It will, okay, and so my design strength is always less than the nominal, so that gets me a little bit of extra capacity. You know, if my member can hold 100 kips, maybe I'm only allowed to design for 90. Okay, so there's a little, so you've got a factor of safety that increases the loads on this side and a factor of safety that decreases the load on this side. That's the heart of what LRFD is. Now the questions that we have is, well, where do these RU values come from? Okay, well, it depends on the loading case, and I can kind of show you a little bit of, give you kind of an example. Most of these come out of design codes. So if we kind of look at this, to give you kind of a sense of our resistance factors, okay, that depending on the cases going on, you know, for many years, phi is taken as 0.9 for bending, okay, and often it's taken as 0.85 or 0.9 for compression, depending on the cases. And these are based off of statistical modeling and confidence interval modeling for risk and reliability practices, which is the basis of what LRFD is. It's a statistical model. Okay, so for example, one of the load cases that we'll often see and that we'll use over and over in this series is this idea of 1.2 times the dead load plus 1.6 times the live load is equal to the factored load on the member. Okay, and so we're going to take whatever the value that came just from the dead loads and then multiply that by 1.2. So we're increasing the dead loads 20%, and we're going to increase the live loads by 1.6 or increase them by 60%. And what these numbers are, these are statistical probabilities or based off of statistical certainties. The idea is that dead loads, I'm fairly confident in where they come from and that they're going to be there at all times. You know, things like self-weight or very heavy pieces of machinery that aren't moved on a regular basis. The weight of a concrete slab are all things that don't move or change frequently. So for that, I'm fairly confident in the positioning. I only have to worry about kind of this 20% increase because my uncertainty level is a lot less. Versus live loads, which could be, cars on a bridge or people inside of a building that move around and at any given time may or may not be there. There's a lot more uncertainty, so there has to be a higher factor associated with those. And that's the basis of this. Now, there's a whole slew of these equations. I've just shown you one of them. I think there's 22 or 23 possible combinations that are prescribed by the code that governs all of this, which is the ASCE SEI 7. Okay, it's the minimum loads for buildings and other structures document that if you're a structural engineer, you need to have this either on your desk or in a PDF form on your computer at all times because you're constantly referring back to this. Okay, my students, we've gotten you access to this as, as part of the class and we'll pull in code requirements from this from time to time, and we did some of this in our last class, but that's where these are all coming from. The International Building Code will reference back to a lot of these same equations, as does the AASHTO Design Manual. This is kind of the grandfather of all of them, although each of these other codes may make their own twist on it or add some to it. This is where we start. Okay, so that's kind of the nature. And we'll show you some more as we kind of move through the process. Okay, again, these are all prescribed by basically by different building codes. Whether it's, again, IBCs are very common on the International Building Code or this or ASCE SEI 7. Okay, now in LRFD, you'll notice if I pull this over a little bit, okay, we'll kind of flip up to some of the other pages. For years, the AISC designs had a bunch of different manuals to cover different design strategies, but starting a couple of editions back, they unified the allowable stress design method with the LRFD method, okay, and came up with this 15th edition book. And it's been 2 or 3 editions that it's been that they've been combined. I think it was the 13th where they combined them. It was a black book, and then it went to the red book. Maybe it's some others in there too, but I think that was where they first unified. They started to unify all those. I don't remember exactly, but it's been several years going on. A couple of decades now that they've been doing these combined. But the idea is that they can do the same design methodologies, and they generalize a lot of stuff in the code. So we've got to be aware of this other one. So anything green in this book corresponds to allowable stress. Anything white in the book corresponds to LRFD. So for this series, we will not be looking at green values, okay? Well, we're going to be looking at LRFD values. And you can see they're fairly significant, all right? So that doesn't mean that LRFD says it holds more load. It just means that the way that you calculate the resistance and the safety factors are different. And we'll kind of show you some of that, okay? So if we kind of go in and we kind of look at this, then just to kind of make us aware of the AST. And again, this is also in that specification right below the section I showed you for LRFD. Okay, you saw a section that looks something kind of like this, that for allowable stress, they're going to say that the allowable stress or the required strength of the member had to be less than or equal to the nominal strength as it was described, okay, divided by some global safety factor. So if I rearrange this, this means that this was omega times RA was less than or equal to Rn is kind of what we do if we rearrange this formula. And omega is always a value greater than 1. And it actually, depending on the phenomenon, and this is the same thing as what we were seeing back with the phi factors, for the phi factors, depending on how it was loaded, whether it was bending or compression or tension or torsion or shear or whatever, these values change. That's the same thing in allowable stress, except in allowable stress, they're going to take it as if it's a rupture case, such as what you might find in connections, that we're going to take omega as 2.0. We're going to double the load that's required basically to design for a member that will hold double the load that's actually on it. Okay, and then for a yielding criterion, then omega is equal to 1.67, which is for yielding. So both of these cases are greater than 1. Okay, and so for many years even you could just take a global factor of safety of 3.0 and cover all cases, and you would go off to the races. Now again, whether that's theoretically accurate or not, I don't know, but a lot of design firms would set a limit of 3.0 and say, okay, now we're covered, cheap insurance, so to say, if you will, as we start to kind of look at that. And you can kind of take a look at it. So that 1.67, if you come back and kind of look at one of the numbers that I had on there, and just on the case that we're looking at, take a look at these two values. It's a very short value, right? 184 to 122 is about 1.5, 1.6. So that's kind of in the realm of what we're seeing on the comparison between LRFD and ASD. So what happens with LRFD and ASD is that the reason that it came about was that they started doing statistical studies of sizes of members and things when they were developing the methodology, and they were finding that in some cases, generally speaking, the results from an allowable stress member versus a load and resistance factor member are comparable. You might be one size difference on those, and allowable stress was typically just a hair heavier. Not always, but a lot of times they give you the same member selection when you're doing design. But it was a way to get just a little bit of economic savings if we were willing to do the extra work to split out the dead load and the live load separately. So this is a new concept. You probably didn't see this in your mechanics and materials. You probably saw this guy, where you had a factor of safety of 3 or a factor of safety of 4 or whatever, a single factor of safety. You knew it was an allowable stress. Okay, but for LRFD, we're going to do it a little bit differently. We're going to factor the loads, and then we're going to turn around and we're going to reduce the capacity. And so it'll give us a little bit of a more accuracy and savings based off of experimental research and our confidence levels in the performance of the member under the types of loads that we're dealing with. So anyway, I hope that kind of gives you kind of an overview of some of the major assumptions that we're dealing with, as well as the basic design methodologies. Okay, so again, we're going to be dealing with load and resistance factor design. So you're going to see us write equations that look like this over and over and over. Okay, and that came straight out of the code. I showed it to you. So anyway, hope it made sense. If you got any questions, as always, leave us some comments down below. Otherwise, be sure to like and subscribe to the video, and we will see you next time. Have a great evening. Happy engineering.